Okay, so in this chapter, we are going to learn about probability. It is probability by itself is a pretty detailed topic. Actually, there are courses which are devoted to probability, not just one course, maybe several of them. If you do like, higher level statistics courses, you may have to, like maybe take 1 or 2 semesters of probability. Okay, but here this class being like a basic stat class, we are not going to go into details in probability, but just get a very basic idea. Okay, all right, so let's go to the next slide. um, Now, so in this chapter we are going to talk about probability, and then we are going to I'm going to introduce a new concept called random variables. Then there are two types of them, discrete and continuous, so we'll talk about them, and also rules and properties of probability. Okay, all right then. So let's go to the next slide. Now in here, this is kind of this chapter is a little bit technical. So when you deal with a technical subject, you must be knowing, we need to know terms. So we need to become familiar with terms. So I think it's a good idea to start with definitions. And then, of course, you may have to go over this chapter a little bit more than, maybe just not more than one, just not only once or twice, maybe at least 3, 4 times. Okay. All right. So let me first of all talk about a random variable. Now, actually, we will be talking more about this in a later slide. So I'm just going to go past this. But random variable is just a numerical quantity. Um, you know, that means it is an x. Actually speaking, like in algebra, it is an x. Okay, like in algebra word problems, you may come across weight, height, and so forth. Okay, so this is an x. Only difference is that it's we in addition to the value it takes, we are going to associate a probability. I mean, I still haven't spoken about probability in here. We are going to associate the likelihood or the chance that x will take certain values. What is the chance that x equals 1? What is the chance that x equals 2? And so forth. So if you have that likelihood for a certain variable, now such a variable is called a random variable, because the values it takes are random. Okay, all right then. So now in fact yeah, we will be talking about more of random variables in a later chapter. So now again, let me go over some of the things that we have done before. Population is a set of all possible values for a random variable. Remember, measurements are x's, so population will be the set of all these measurements. Okay. Event is an outcome or set of outcomes. So that would be, again, now we will be we'll talk a little bit more about this. If you think about tossing a coin, you have only two possible outcomes, right? Heads or tails. So events are the possible outcomes. If you roll a dice, you can get zero. I'm sorry, you can get 1, 2, 3, 4, 5, 6. So as it is, I have mentioned 6 events, but there could be even other events. Actually, to see or to observe an odd number when you roll a dice. So that is an event itself. Okay, so you could have lots of different events. When you talk about any situation. Okay, all right. Now typically events are denoted by capital letters. And then once you have defined the event, you can talk about its probability. And then probability of an event A, here's another piece of terminology, P within paren A. Okay, probability of an event B will be P within parenthesis B. Now, how do you calculate probability of A? It is the proportion of times an event is expected to occur in the population. Okay, now, so it will be like little n over big N, where n is the total number of possible outcomes and n is the number which is favoring that event. Kind of, sounds technical, but it's really not a big deal. Let's look in here. Probability of an odd number when rolling a dice. So what is n here? N is 6, because the total possible number of outcomes is 6. Either you can say 1, 2, 3, 4, 5, 6, right? And then how many will be favoring this particular event of the number being odd? 3 of them. Okay, so it will be either 1 or 3 or 5. So 3 of them, so it's 3 over 6, 1/2. Of course, intuitively your common sense tells that there's a half percent chance, 50% chance that you will see an odd number. Now, actually speaking, we talked about relative frequencies in the previous chapter. See, actually, relative frequencies are like an approximation to probability. I have given an example in here. Let's look in here. Now, if you, in a community, you sample 50 people, and then you ask whether they smoke or not, right? And then you find out that there are 10 smokers. So then, what is the relative frequency of finding a smoker? It is 10 over 50, which is 20%. And then you can say that the probability that a randomly chosen person in that community is a smoker is approximately 20%. Now, why did I say approximately here? You never can get the exact value by this method of relative frequency. And as you improve or as you increase n, you will get the value to be reaching the exact probability much better. Okay, here of course we took only 50, but in a community you will have many more, right? There could be thousands. So this is a very poor approximation in fact. Okay, but the fact is that relative frequencies are approximations to probabilities, and as you keep on increasing the sample size, the relative frequency approaches the actual probability. Okay, all right, next slide. So here, in fact, another illustration. So they have, there were this many number of traffic fatalities in a population of this many large numbers. I don't want to tell how much it is. Okay, so you just take the relative frequency, this number divided by this number, which they have done in here. Relative frequency of this event in the population is this, very, very small proportion. So probability of a traffic fatality, that was the event, right? Event, these are the number favoring that event. So that is why you have that in the numerator divided by the total number n. And then, so then you will get the probability to be approximately this. Okay, not exactly, approximately. But this approximation is pretty good because n is pretty large. Okay, all right then. Let's go to the next one. Okay, now probability as a repetitive process. Now see, in the previous example, it was like a empirical, it is like you observed and then you found the probability. Now you can think of probability as that you can create out of a process where you do it over and over and over. Okay. Now in fact, if you sort of have a population where 20% of the observations are positives, okay, I mean positives could be lots of different things, maybe having a disease, maybe what else, maybe being a smoker, and all kinds of things. Okay, so in the population, if you know that 20% are positives, okay, if you take a sample and then calculate the sample proportion of positives, as you increase the sample size, that sample proportion, which is a relative proportion for the sample, will reach 20%. So in fact, it will be evident to you from the plot here in this slide. So if you start with like, so in that population where you expect 20% to be positives, if you have n to be 10, that means you're having only 10 people, the probability is a little bit high. See, it keeps on varying. Just look how much variability is there in this area because n is not large enough. But as you keep on increasing n into the 10,000s or even like 1,000, somewhere from like 1,000 on, it is very stable and is actually equal to 0.2, which is 20%. and that is the actual probability value. Okay. Now see characteristics. As I said, in the previous example or previous slide, they talk about positives. Now positives is some characteristic. It is just a code for a certain characteristic. It could be like smoking. It could be being diabetic. It could be being obese and so forth. Now, by the way, since this is a biostat class, I'm always trying my best to go use, health related examples. Okay, so let's go to the next one. Now, there's another probability called subjective probability. It is like you sort of you attach probabilities. If something is really seldom, you will tell, okay, there's only a 5% chance. Okay, now, as an example, now say, so these are like the categories of events, like the likelihood of events. An event can be seldom, an event can be infrequent, and so forth. So if you have, so this is sort of like a rough rule of thumb. So, for example, here I have put an example in here. Snowing in December in Pennsylvania is very highly likely. It could be that, but not 100% sure, but very highly likely. So you can say that, okay, there is like a 95% probability of snowing in December in Pennsylvania. It is because this event of snowing in December in Pennsylvania is, we think from our experience, that it is highly likely. Okay. Now, this kind of thing we do in our everyday life, attaching probabilities to, events that we know or that we come across. Okay. Now, these ideas will come in later. There is a branch of probability called Bayesian, where you use this subjective probability and improve that using data as well. Okay. All right. So let's go to the next slide. Okay. So here we are talking about random variables. Now this is the beginning. So probability, we got a rough idea. So random variable, as we said, is a numerical quantity. It is an X, so it will take values. But for each value that X can take, there is some chance behind it or chance associated with it. Now here's the example I did. Say you toss a coin 3 times. Now there are 8 possible outcomes, which I have listed for you here. You see H stands for heads and T stands for tails, obvious, right? So you can either get 3 heads or 2 heads the first and the second time, and the last one to be tails, like that. Okay, and then you can get all 3 tails. Okay, now once you have that, I'm going to define X to be the number of heads, because you will toss the coin 3 times and you will either get all 3 heads, just 2 of them, just again another 2. Of course, this is in a different way. Here you get heads the first and the third toss, right? So now X is the number of heads. Now X is a random variable. And what are the possible values for X? You can have no heads, like in this particular case, TTT, no heads. 1 head, like in let's say like in here or in here. Oh, sorry, like in here and in here. There's only 1 head in this particular outcome. There is only 1 head. Or you could have 2 heads. 2 heads. Let's see. Did I do it correctly? Oh, this should be yeah. So actually, you could have 1 head in how many? This, and also this. You can have it 3 times, right? And you can have 2 heads here, here, and here, or you can have all 3 heads. So now, so the possibilities are 0, 1, 2, and 3. Now here's a mistake, typo. Also, there is chance involved in X taking any of these values. So what's the chance that X equals 0? It corresponds to this particular outcome. What's the chance that you will get all 3 tails? 1/8, because there are altogether 8 outcomes. All of them have the equal chance of happening. So this one is 1/8. Now, likewise, I guess you guys can fill this in, right? Probability of X equals 2 means 2 heads. So it will be this, this, and this. So there are 3 possibilities favoring that event. So it will be 3/8, right? So let me put that answer in here, and you can finish the rest of it. Okay. All right. Let's go to the next slide. Oh, wait a minute. I did not finish. So random variable example is right here. Now, when you talk about random variables, there are two types of random variables: discrete random variables and continuous random variables. Now, discrete, actually, this is, in simple words, this is always count data. Okay, count data. Like, number of errors, number of cancer patients per month. Okay, number of flu cases in a school. So stuff like, it's almost always, for this course, it is very safe to assume that discrete random variables are always count data. Okay. All right. Now, continuous random variables are, they are variables which can take any value in a given specified range, like weight. See, weight of a newborn could be maybe from, I don't know, 6 pounds to 12 pounds, the normal newborn. So it could be the baby's birth weight could be 6.2233, anything, but we may not be able to even see it if you use a weighing scale. But nevertheless, any value in between 6 to 12 pounds is possible for a baby's birth weight. Okay, so this is like a continuous random variables. In fact, I'm sure most of you have done calculus. Now you know what continuous functions are. When you have a continuous function, the curve has no breaks, right? So the continuous random variable is similar to that. If you draw the possibilities for the continuous random variable, there will be no breaks in the given range. Okay, so I mean, this should be clear intuitively. And then discrete random variables is just count data. All right. Okay, let's go to the next one. So okay, so probability, discrete random variable. Now when we talk in detail about this, we need to understand what the probability mass function of a discrete random variable is. Now the abbreviation for that is PMF. So discrete means it takes only specific values. See, in a very informal way, I sort of tell students, think of as if these values x can take, there are gaps. See, there's gap between 1 and 2, like 1.5, 1.6. In continuous variables, no. All the numbers in between are possible. Here, no, there are gaps. Okay. So think of it that way. So you can distinctly write them separately, unlike in a continuous case. So then you can write them down, and then you can find the probability that x is, each of these x is equal to that particular value. Okay. So now, of course, how you find this is sometimes maybe these values are relative frequencies. Okay, these are the approximations in terms of relative frequencies. Okay, or like in the previous class where we did the coin tossing experiment, it is a very theoretical experiment. We had x equals 0, 1, 2, 3, remember? And then x equals 0 was 3, let's see, 1/8 for no heads. X equals 1 was 3/8. Like that, we can figure it out, like if you have a theoretical situation by mathematically arguing it out. Okay, lots of times, of course, empirically, by means of the relative frequency, we can calculate these as well. That's what is being done in here. Okay. So here's the PMF. Now, also remember, when you add all these probabilities, it should add to 1. Okay, so you can even check it yourself. I will write it in here. All PMF values add to 1. Okay, because given given x should equal to one of them. Okay, so that is why PMF should add to 1. Okay, now PMFs can be represented by sort of like a graph like this. See, these are the number of possibilities, and then and then you can just list them like this. Okay. Um, um, Now probabilities have certain characteristics or properties. Okay. So here are the properties. The first one I said, probabilities are always between 0 and 1. And then the probabilities in the sample space sum to 1. Now, what is a sample space? Sample space will be all possible outcomes. Now, like in the first example we did in the coin tossing experiment, we tossed the coin 3 times. The sample space will be, all those possible 8 outcomes. Okay. Um, and then, so the probabilities will add to 1. Then the complement of an event, that is the event not happening, will have the probability to be 1 minus the probability of the event. And then also the complement is denoted by a bar on top, okay. So if you think of like a to be an odd number, a bar will be an even number. So probability of an odd number in rolling a dice was 1/2. So using this equation, you can say probability of getting an odd number will be 1 minus 1/2, the other half. I mean, you know that intuitively, both probability of odds and even will be 1/2. It's sort of like if you know that, okay, if say let's label A to be raining today. So the weatherman tells you that, okay, there is a 30% chance that it will rain. So what is A bar? A bar, the event, is not rain. What is the probability of not rain? 30% is rain, so 1 minus 30 is 70%. Okay, it's a very intuitively clear idea, but very, very important, very useful as well. Because sometimes it will be very easy to calculate probability of A, but not this. But once you have it, you 1 minus it, then you get the answer. Okay? All right. Now, then property 4 will be probabilities of disjoint events can be added. Disjoint means if A happens, B does not happen. Okay? That means like even and odd. Okay? Those are disjoint. Then you can have, the probabilities to be added. Okay? Now, let me write down if you have A to be a science major, and B to be a male, okay? Now, are A and B disjoint? No, right? Because, there are male science majors, right? Okay, so not all pairs of events are disjoint, but if you have, if there are, then you can add their probabilities. Okay, let me get rid of this science major. All right. Okay, so let's get, so here we learned 2 useful results, and then let's go to the next one. Okay, so in terms of symbols, you know, in this slide, what is done is, pretty much writing what we learned in the previous slide, and then, everything is written in terms of symbols. Okay. All right, let's go to the next one. Yeah, now actually, if you refer back to the figure 5.2 in the textbook, you will see an illustration of this. You may go over it. If you have any questions, please email me. Okay. Okay, so property 3 illustrated. Now, property 3 is probability that the complement probability is 1 minus the probability of A. In fact, here, look, you take the event A to be 4 successes. If A is 4 successors, you know that probability of A is 0.3164. So now, what is A bar if A is 4 successors? A bar which is not A is fewer than 4 successors, okay, or three or fewer successors. So 3 or fewer will be this plus this plus this, and also this. It's a sum of all these. But see, rather than do this, it's much easier just to subtract this from 1, and then you get the answer. And actually, if you do the long method, also you will get the same answer, okay? So now something like this, like here, of course, you have only 4 things. Not 4, I'm sorry, 5 things. What if you have 50? Rather than adding up all these 49, it's much better to do 1 minus, right? So this result is very useful. Okay, then. Now property 4 illustrated. Now here they take event A to be 4 successors, B to be 3 successors. Now see, if there are 4 successors, you cannot have 3 successors, right? So A and B are disjoint. So if you want to find the probability that there are 3 or 4 successors, you just add the probability of 4 successors plus probability of 3 successors, right? Makes sense. So, that's what that result was telling, which is pretty intuitively clear, okay? All right, now we come to a little bit more theoretical results. Okay, now we talked about discrete random variables. Now here, these apply to discrete random variables, okay, like count data. We will, here's a definition for the mean. Remember, we talked about mean for the data, and we talked about the population mean. Now, this is like the theoretical model for a population mean. So if you want to find the population mean, which the symbol is mu, we learned about it even previously, what you do is you take the possible values, which is denoted by x, and you multiply it by probability that x equals little x. Okay, so this is the formula that you are going to use, to find the mean value for a discrete random variable. Okay, all right then. And then likewise, remember we talked about variance. Now to get the variance, we need to use this formula. In fact, there is another shortcut formula, in my opinion, which I will show you. And we will be in fact doing an example. Okay, so I think I'm going to break this lecture up at this point, and then record the remaining in another presentation. Okay, all right then. So this is actually chapter 5 part 1.